Hey guys, so this is going to be the second video for chapter 15, Descriptive Statistics. I am going to try to um, get through this in as quick and concise way as I can because there's a lot of information to cover here, but I don't want you guys to have to watch a really long video. So this is going to address learning objectives 3, 4, 5, and 6. That should tell you we're covering a lot of material, which is going to talk about constructing frequency distribution tables or graphs to organize and display an entire distribution of scores. We're going to define and compute 3 means of central tendency, or learn how to do that, or what that means. We're going to discuss how the mean and standard deviation describe a distribution of scores, and how Pearson correlations describe the relationship between two variables and predict the general appearance of a scatter plot for data. Okay, there's 2 general techniques for organizing or summarizing a set of scores, which, remember, that's the definition of descriptive statistics, is to organize and summarize a set of scores from a sample. When you are organizing, so there's two general techniques here. One is organizing the entire set into a table or a graph to see the whole set of scores together, like a kind of a visual representation, right? But there's also a second technique is to compute 1 or 2 summary values, like an average, that can describe the entire group of scores. Okay, so first we're going to talk about the first technique, which is organizing that entire set into a table or a graph to see the whole set. So that is called a frequency distribution, is the first thing we're going to discuss here. Frequency distributions, again, simplifying, organizing set of scores. We're grouping them into an organized display. It consists of 2 columns. One is the scale of measurement, or the type of scores, or it just depends on what exactly the frequency, what exactly the data is. And then the second column is the actual frequency of the number of participants in each category or each score or whatever. That'll make more sense when we look at this table in just a second. The advantages of a frequency distribution are that, or an advantage is that you can view the entire set of data quickly and concisely, but the disadvantage is that it can be tedious or time consuming or hard to have an entire frequency distribution of a large set of data, especially if you don't have a computer program to do it for you. If you're doing it by hand, that can be kind of hard. These days, of course, we typically have computer programs that can do it for us. So this is a table showing a distribution of scores from a 5-point quiz. This is table 15.1 in your book. So you see the first column is labeled X, which means that's the score. That's the type of score they could have scored on this 5-point quiz. So and that's why it's called categories, because they either scored a 5 or a 4 or a 3 or a 2 or a 1 or a 0. They couldn't have scored multiple things, right? So whatever their score was on this 5-point quiz is there. And then the F category or column is the distribution. The frequency. Good grief, I can't talk today. F for frequency. And what that means is the number of times that score occurred, or the number of participants that scored that score. So in this table, you can see one person scored a score of 5 on the quiz. 3 people scored a score of 4. 4 people scored a score of 3. I'm just going down the F column. 3 people scored a score of 2. 2 people scored a score of 1, and 2 people scored a score of 0. So you see how that works. You can also graph frequency distributions if you don't want to do a table. If you want a more visual representation, you can do graphs. So for interval and ratio data, this is what your 2 graph options would look like. You could do a histogram or you could do a polygon. This is figure 15.1 from your book. You can, if you notice, the x-axis or the horizontal axis here is the scores, those categories or possible scores for that 5-point quiz. And then you notice that the y-axis or the vertical axis is labeled F, that's the frequency. So the height of the bars or the polygon is determined by how often that score occurred or how many people scored that particular score. You'll notice that on the histogram, the bars are touching. And some of you might have thought, hey, I thought that was called a bar graph. Well, this is not, because the bars are touching each other. It is a histogram. The reason that they're touching and it's called a histogram is because those numbers down there, it's numerical, it's continuous. So, 0, 1, 2, 3, 4, it's not a category, that's a continuous score, right? If you look at this is a bar graph, and you see they're separated because they are completely independent of each other. It is not a continuous number thing. These are categories. So they are not touching. This bar graph is an example of what you would do for frequency distribution for nominal or ordinal data. Remember, that's those categories. So it's non-numerical data. It's not numbers that you measured. You are, I'm sorry, they're categories that you were interested in, not numbers. And so this example is the majors that were in an intro to psych class. And so you can see from this visually that there were 10 psych majors, there were 6 biology majors, there were, looks like probably 3 English majors, looks like 8 or 9 education majors, 6 business majors, and 4 math majors, just from looking at that. And obviously visually that gives you a great way to look at the data, because you can see that English majors were the least and that psych majors were the most. And you can see things like that visually very easily with these types of graphs. Frequency distribution is really a preliminary method of statistical analysis. And so it may be the first thing that you do once you have your data set, just to kind of get your bearings, but it isn't really shown much in published research reports because there's so much more you can do that's going to reveal more information. Some people will include it, but a lot of people won't. This is more of a behind the scenes great first step of what you do with your data, just to, like I said, get your bearings and figure out where you want to go next with your analysis. Okay, so there are other simpler methods for describing scores in a sample besides frequency distribution. One of those are measures of central tendency. And so for interval, this is obviously for just interval and ratio data. Okay. Again, these are all descriptive statistics. We are describing the data set. For interval and ratio data, again, numerical scores, we can do measures of central tendency. The most common measure of central tendency that you know is the average, but we're going to talk about 2 others. Central tendency is identifying a single score that is defining the centerness of a distribution, which basically means we're trying to identify the value that is most representative of the entire group, so that we can say, this value, again, describes in essence the entire group. It is either the most typical or the most representative number, and the average is usually a great way to do that. Mathematically, it is called the mean. Hopefully you've heard that before. But mean, average, same thing. As far as mathematically, the mathematical average is calculated, as you probably know, by adding all the scores up and dividing by the number of scores. It is usually represented by an X with a horizontal line above it, and that is usually called X bar, and that is the symbol that if you see that in research, that is talking about the average or the mean of the score. That's the most common used measure of central tendency for numerical scores, obviously. That's why you've heard of it. But Sometimes there's situations where you can't calculate the mean, or the mean isn't representative. Remember, we want it to be that most representative of the entire group, and sometimes it's not. Those cases are when there's extreme scores. So that maybe there's like a couple scores that are really, really high, unlike the rest of the distribution, or really, really low, unlike the rest of the distribution, and that throws off your average, right? That makes your average higher or lower than it really should be. And so when you report, if you were to report that mean, it would look like the distribution of scores, or the, average score for the group is a lot higher than it truly is. Most of the people scored in a different, range. And so sometimes when you can't use the mean in those situations, you need to use the median or the mode. The median literally cuts the distribution in half. What that means is you order the scores from least to greatest, and you literally find the middle point. So if you had 20 scores, then you would find the 10th score in the list and the 11th score in the list, and you'd have to average them together because there's an even number of scores. If there were 19 scores, then you would just find the 10 points, and that you would know that there are 9 scores above it and 9 scores below it. So it is the direct middle of the data. And so that score would be the middle point. And so that number would be your median. Okay. The mode is literally just the most common occurring score. So in the frequency distribution we looked at, it would be the highest point. So for here, it would be the score of 3 was the highest point, is the peak of the graph. And so that is the most commonly occurring score, was a score of 3 for that particular data set. For categories, you have to use mode. So for here, you have to use mode, because you can't calculate a mean, and a median is impossible, because those are not numerical categories. They're not numerical data. It's categories, right? It's majors. And so mode is the only measure of standard tendency you can do. So you would say the mode is 10 here, or is the psychology majors was the most common major in the intro to psych class. The mode is also often reported with the mean, to kind of give you an idea of the shape of the distribution, because if it doesn't match up with the mean very closely, that means that the shape of the distribution is varied a lot. Whereas if the mode is very similar to the mean, then that means that the scores don't vary quite as much, and the shape is more typical. I hate to use the word typical, or normal. Okay, so another measure that you can use to describe, another statistic you can use to describe your numerical data, is standard deviation. You've probably seen that or heard that in some of the research that you have read. It is the square root of the variance. Well, what's the variance? We'll talk about that in a second, but it really is just measuring the variability of the scores. So how spread out those scores are. It does that by describing the average distance from the mean. So the standard deviation is the average distance that a score is from the mean or from the average. It's showing you how those scores are scattered around the mean. If they're really, really spread out around the mean, or if they're really, really close to the mean, it helps show that. As a general rule, just to kind of give you an idea of what standard deviation means and like helps you understand, roughly 70% of scores will fall within one standard deviation, usually, of the mean. So one standard deviation away is usually going to be within one standard deviation above the mean and one standard deviation below the mean. You're going to have about 70% of your scores. 95% of your scores are going to fall between two standard deviations above and below the mean. And so that just kind of gives you an idea. When a report says that the standard deviation is 4 for a set of data, well, that means that excuse me, that the average distance that a score is from the mean is 4. So that would give you an idea of that. If, let's say, the mean was 10, well, then that would mean that if the average is 10, then, and the average distance is 4, that would mean that 70% of your scores are falling between 14 and 6, right? Because that's 4 above and 4 below the average of 10. So 70% of your scores are going to be between 6 and 14. And 95% of your scores are going to be between 2 and 18. Okay, so that kind of gives you an idea of how spread out the scores are, and kind of the range of the data as well. Variance, as we talked about a second ago, is just the square root. Is the standard deviation squared. So that's why we take the square root to get the standard deviation. So variance itself isn't usually reported because it doesn't mean a whole lot, because standard deviation is what means the average distance. So we usually talk about standard deviation, but variance is used in a lot of calculations for statistics. So it is the average squared distance is what we would say from the mean. So to find variance in standard deviation, you have to make a column of all your scores. Then you would, in the column next to it, you would find the distance from the mean for each score, which is often called deviations. Distances, deviations is the same thing. So let's say your mean is, like I said, let's say your mean is 10, and your score is 12. Well, then your distance or your deviation would be 2, because there's 2 between 10 and 12, right? And so you measure the distance between the mean and the score, and that's your second column would be all of the distances or deviations, right, from the mean. Then you would make a third column and you would square all those distances. Okay, so that 2, you would take it, you would square it, make it 4, and you would do that all the way down the column. And then you add all of those squared distances or squared deviations up, and that gives you a larger number. Then you find the average squared distance, right? Because we got squared distances, we're going to find the average squared distance by dividing by the sum of those square differences, meaning what? Dividing the sum. Oh, I'm sorry. I read that wrong. I'm like, that doesn't make sense. I thought it was typed wrong. No, I just read it wrong. We're going to divide the sum of the square distances by, normally you would divide by the number of scores, right? That's how you find an average. But for statistics, for variance, you're going to divide by n, that lowercase n is the number of scores in your sample, or the number of participants in your sample. You're going to subtract 1 from that and then divide. The reason you do that, the reason you're dividing by 1 less than the number of scores is, we're going to talk about this a little bit and more in a second, but that's really providing a more accurate, the variance will be more accurate, your standard deviation will be more accurate that way, because this is a sample, and our goal here, right, is to generalize to a population. And in general, the samples, the variability in the sample is a little bit different than the population because of error or because it's just smaller or whatever. And so the n-1 makes your variation or standard deviation or whatever your statistical calculation is more accurate for applying it to the population. So when you average that, those squared distances, you get the variance, which is often S, a lowercase s squared, is usually the symbol that is what is labeling variance. To find the standard deviation, you just take the square root of that. And so it would just be a lowercase s. So standard deviation is a lowercase s in most textbooks. And that tells you your standard deviation. Or again, the average distance from the mean that a score is. In published research reports, standard deviation is usually reported as a capital S and a capital D together. So SD is usually standard deviation in published reports. Now, back to this N-1 for a second. That is called degrees of freedom. There's a lot more detail we can go into about that, but just know that without taking that one away, without the degrees of freedom there, we underestimate that population variance, as I mentioned. We're underestimating what the population variance actually would be. And so in order to make it a more accurate and unbiased representation of the population, when we're calculating our sample statistics, we're going to take one away from the total number of scores when we do our calculations, and that's called degrees of freedom. There are examples of the measures of central tendency, the mean, median, and mode. There's examples of the calculations for standard deviation and variance, all in Appendix B in your book, if you want to see actual examples of those calculations. Okay, so now, what if it's not numerical data? What if it's nominal or ordinal scales, those categories? Then what do we do? Often those data, that doesn't make sense. Those data are described using percentages, proportions, or the mode, as we talked about a minute ago. So just to refresh your memory of nominal and ordinal scales, these would be things like level of education, like whether they're a college graduate or not. That's a label. They graduated or they didn't. Or an attitude where they are agreeing or disagreeing. So they either agree or disagree. It's a category, right? Or self-esteem levels, you would say high, medium, and low, like high self-esteem, medium, low. Those are categories, right? That's not a numerical data. So for proportions or percentages, those are things like 43% of the sample preferred this candidate and 24% of the sample preferred this candidate. Or you could say 80% of 6-year-olds completed this, of the 6-year-olds completed the task, and 40% of the 4-year-olds completed this task. So things like that. That is often how that is described when it's non-numerical data. For the mode, again, that's the most popular or most commonly occurring score or answer. And so, again, measures of variability are impossible for one, because you can't calculate, but also they're meaningless. There's no distance between scores here. And so, because there's not scores, these are categories. And so these are the 3 typical ways that non-numerical data is reported. Okay, so what about graphs? If we want to use graphs to compare groups of scores. So before we've been, describing the shape of the scores and all of that, but what if we want to compare groups of scores? It is common to use a graph to display the summary statistics for all the different groups being compared so that we can quickly and easily see how the groups compare. So it can allow several different statistics. I can't talk today, I'm sorry. To be displayed all at the same time so that somebody can easily see the differences or the similarities between the groups. The most common way this happens is sample means, is graphing the means for each group. The graph can either be a line graph or a bar graph, which we will look at in a second. But basically, well, here, no, I'm actually going to show you guys already so that you guys don't have to listen to me and not know what the heck I'm talking about. So in figure, it's right here, 15.3, I already had it up there. This is showing you the top one is a line graph, the bottom is a bar graph, obviously. And this is showing you those sample mean graphs. Notice that the x-axis or that horizontal axis are the levels of the independent variable or the treatment conditions or the groups that they were assigned to, depending on the type of data or the type of research design you used. So the top graph, it's drug doses, 10 cc's, 20 cc's, 30 cc's, you see that. And then the bottom graph is a teaching method. So there's 4 different teaching methods that they used. They were either assigned to the first teaching method, second teaching method, whatever. And then the y-axis is the values or the sample means that are being compared. So you see mean activity level is in the top graph, and the second one is mean reading achievement score. And so you can see that the mean for the 10 cc drug dose group was 2 for their activity level. And the drug dose cc 20 cc group, the mean score for that group was 4. Okay, and then down at the bottom, same thing. Teaching method 1, that mean for that group was 8, and the mean reading achievement score for the second teaching method was 10. And so you can see how you can compare those pretty easily and see in the top graph, 30 cc's seem to have the most activity level. And you can also see that 40 cc's and 20 cc's are kind of close. In graph B, you can see that the second teaching method seemed to be the most effective. The third teaching method was obviously the least effective. So it's a really easy, quick visual way to see how your groups compare. This is for sample means. Now, you can also do median or proportions. Again, because if you have different types of data, if you have, non-numerical data or situations where you're using the mean instead of the mean, the median instead of the mean. I think I said that weird. Or if you're using proportions because it is nominal or ordinal data, you can still graph that in bar graphs or line graphs. And so that would be in figure 15.4 here. You can see that the categories, again, are on the x-axis. So there's high school, college, or postgraduate level of education. And you can see the median income in thousands. So high school, the median income looks like it's about 15,000. College is 40,000, and postgraduate is 45,000, close to 50. I don't know. It's hard to tell. But you can see visually very easily that postgraduate has higher income, right? Higher median income. For the bottom graph, it's age. The 18 to 29-year-olds, 50% preferred digital. I don't know exactly what this study is, but you can see that the highest proportion was for the 18 to 29-year-old age group, and the lowest was for the 50 to 69-year-old group. Obviously, that makes sense because it's something digital, and so the younger age groups can be more familiar with technology. So that makes sense. And so that's another way of showing you the graphs for that. The format is the same. It's just a little bit different because of the categorical data. Okay, so figure, oh wait, let me go back. Figure 15.5 is going to show you, so for factorial designs, like we talked about in chapter 11, I believe, that's when we have two or more independent variables. And so you have to have that matrix there, because here we have two independent variables. We have temperature, but we also have humidity, and we want to know how that affected performance. Our dependent variable was performance. So you have to have a matrix of scores or of means there for factorial design. And so how would you graph that? Well, this is the graph that I was talking about before with your quiz, where I talked about how you can look to see if there's an interaction between and your main effects and all of that. This is the line graph that I was talking about for that. So you see that your y-axis is still your means, right? Your x-axis is just going to be one of those independent variables, right? We can't put both on the same axis. So it's temperature. Okay, the two different lines, they've made them red and blue. The two different lines there is your second independent variable. So what you do is you match them up. So if we go on the matrix and we do low humidity and 70-degree temperature, the mean was 30. So what we do is we make that data point. We go to 70 on the x-axis, we go up to 30, and we make that point, but we make it blue because it's low humidity. Okay, and so if we just go across the low humidity to make our line, we're going to see that when we go across the x-axis, 80-degree temperature has to go down to 28, and then 90-degree temperature has to go down to 24 because the mean was 24 for low humidity and 90-degree temperature. Okay, and then we connect them and we make a line, and that's the low humidity line. Same thing with high humidity. We go with 70, we go up to 28, and then we go down to 20, and then we go down to 12. As we go across the matrix and as we go across the x-axis, we just make those data points, and then we draw that line. And so you can see that they're heading in the same direction. If we kept drawing those lines, if we had more measurements, they would eventually connect. They would eventually cross. And so they're moving towards each other. They are not parallel. So there is an interaction here between temperature and humidity. And that's kind of what I was trying to show you guys before. That's not the point of this chapter, but this is a great example of that. And since I had talked about that in the last video, your feedback video for week 6, I wanted to bring that up. Okay. So there's also correlations. That is also descriptive statistics. That is a way to describe the data in a different way. And so correlations, this is mostly a review, as you guys know. We talked about that a lot in chapter 10, but and other chapters too. We've talked about correlations, but so you guys know that correlations are defining relationships between two variables, right? Well, just as a reminder, we talked about this before, but there's a difference between, you can evaluate the relationship between two variables like self-esteem and performance here in table 15.2. You can do this in two different ways. You can do a differential study where you're actually comparing two groups, so it seems more like experimental, and the difference between the means. So you see here, we have a mean for the high self-esteem group. I'm on the top part here, A. The mean for the high self-esteem group is 20.5. The mean for low self-esteem group is 13.75. We can compare those means, compare the means for the groups, and that tells us about the relationship. That tells us that the high self-esteem group performed better than the low self-esteem group, right? That tells us about the relationship between self-esteem and performance, that high self-esteem improved performance or led to higher scores. The other way that you can evaluate the relationship between two variables like self-esteem and performance would be a correlation. And that we're not comparing groups, right? We're getting out of that category. We're not comparing groups anymore. We have measurements for both variables. So for participant A, down here at the bottom, we have a self-esteem score and a performance score. So you have two sets of scores for both participants, and then we compare, we calculate the correlation between those two, and that correlation describes the relationship between the performance. And so I think the correlation here ends up being like 0.8 something or 0.9 something or whatever. And so that would tell us that the higher the self-esteem, the higher the performance. As self-esteem increases, so does performance, right? That tells us about the relationship via a correlation. So the two variables are usually identified as X and Y. So self-esteem would be X and performance would be Y, for example, so that it can be presented in a table or a scatter plot. The measures, they measure and describe three aspects of the relationship between two variables. Remember, we talked about this in chapter 12, where there's the direction of the relationship, which either means it's a negative correlation or a positive correlation. The form of the relationship, most often it's a linear relationship a lot of times, and so it's Pearson correlation that's commonly used, which is that lowercase r. And then there's the degree of consistency or strength of the relationship, which is the value of that number, of that correlation. So if it's 0.85 and negative 0.85 correlations would be equally strong. They're both strong because they're close to 1. The difference is that one is a positive relationship, meaning that as one goes up, so does the other, or as one goes down, so does the other, or it's a negative strong relationship, or a strong negative relationship, meaning as one goes up, the other goes down. They move in opposite directions. That's what the negative means, remember. It does not mean weak. It means that there is a difference in the way they are related. Examples of calculations of correlations, again, are in Appendix B. And then you also have regression. And so let me make sure I calculated all of that. Oh, wait, hold on. Before we get to regression, I was going to show you guys 15.6, the scatter plot. Again, the self-esteem is along the x-axis, the task performance is along the y-axis, and you can see all the data points. So the person with the self-esteem score of 62 scored a 13 on performance. The person with a score of 66 on self-esteem scored an 11 on performance. And so they make that data point for each participant that shows both scores, and then you can see how the data is shaped, and you can see this is a positive relationship again. Oh, there's the value down there at the bottom. It's R. The R is 0.933. That's what I thought. So it's a very strong positive relationship. Okay. Oh, it wants me to know if I'm still there. I am still here. Okay. So regression, really quickly, is just finding that line of best fit that best fits the data. That line that can go through the scatter plot, through those data points. And what it enables you to do is predict one variable from the value of the other variable. So if we have self-esteem score, we could predict their task performance score by using this equation, this line of best fit. The lowercase b is the slope of the line. So in other words, how steep that line is, if it's like close to vertical or if it's more close to horizontal. And then the a, that lowercase a, represents the y-intercept, which is just where that line would cross the vertical y-axis. That second equation with the z underneath that is a standardized version. It's the same thing, it's just standardized. And so scores, what that means is that the scores were converted to z scores first. They were standardized before this line was calculated. And so that's all that means. That fancy looking b there in that equation is equal to your lowercase r, or your correlation in that equation. And also, just a note here is that if you see lowercase r squared, that is just telling you the proportion of the scores on the y-axis, the variance of that. It's the proportion of how that varies that is predicted by that line, by that regression equation. Examples of calculating regression is, again, in your Appendix B. And then there's also multiple regression, again, where sometimes if there's more than one predictor variable, so like if you want to predict college performance, you could just use SAT scores, or you could just use high school GPA, or you could use both, and that would be a better predictor together if you used both GPA in high school and SAT scores to predict college performance. And so if you have two variables there that you're using to predict a third variable, that would be multiple regression. And so the line is called multiple regression equation. It's a similar process. You can see the line equation there looks similar, except we have to have two different b's now. We have to have two different slope numbers because there's two different predictor variables happening. And again, the z is just that standardized version. And if you want to know the proportion of the total variance of those scores that's accounted for by that line or by that equation, that's going to be a capital R squared instead of a lowercase r, because it's multiple regression and not just regular regression. Okay, so that's it for that. Let's do the learning check really quickly and we will be done. We got through it all, guys. Good job. Okay, learning check. The ages of the children in a summer camp range from 7 to 12, and the counselor wants to do a frequency distribution showing the number of children for each of those ages. How many 7-year-olds they have, how many 8-year-olds they have, how many 9-year-olds they have, you get the idea. So what kind of graph would be appropriate for that? Well, you could use either a histogram or a polygon. If you flip back in your slides, if you rewind this video, or if you look back in your book, you can use either of those for this kind of data because it's numerical, it's not categorical, and so you could use either one of those for that. And then for scores measured on a nominal scale of measurement, that category, which like this is jobs classification, which measure of central tendency is appropriate. Remember, that's non-numerical, so you can't calculate anything. So you can't do the mean, you can't do standard deviation. Mode is the most popular. Depending on the type of data, you could possibly do a median, but if it's truly non-numerical, if it's just jobs classification, it's not coded in any way, there's no numbers, then it has to be mode, okay? Mode is the only way that you can find that central tendency. Which of the following is the definition of variance? Remember, variance is standard deviation squared, and standard deviation is the average distance from the mean. So variance is the average squared distance from the mean. And I know some of you probably think that is just crazy, and that sounds crazy, but the further you get into statistics, if you do that, you will understand variance more, and it is very useful in calculations. Last question, what would the scatter plot show for data that produces a Pearson correlation of R equals positive 0.88? Well, it's very close to 1, so it's a strong correlation. It's going to be very close to a line, and it's positive, so it's going to go uphill. So all the points are going to be very close to a line. They're not going to be spread out all over the place. That would mean it was close to 0. Since it's close to 1, it's going to be close to a line, and it's going to go up to the right because it's going to increase as x increases. So that is it for 15.2. Good job, guys, for hanging in there. And if you have any questions, let me know.